Theory notes. It's homecoming week, so we're going to have a little homecoming pirate swag to go with this. Just think of this as our chemistry molecule, since we're going to be talking about the kinetic molecular theory, which really deals with the physical aspects of what the gases are doing when they're colliding with each other, when they're moving around in their kinetic motion. So here's your homecoming swag. All right, let's get going. One of the main tenets of the kinetic molecular theory is that gases are a large number of molecules that are in continuous and random motion, always moving, always random. Another main tenet is that the combined volume of all the molecules of gas is negligible to the total volume. So you have to think of this as very, 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 very small. And even if you got them all together, you really wouldn't see any volume compared to what it was held into. Hard to imagine, but that's what we're trying to do. These guys also don't repel or attract each other at all. So therefore, they just do act like little balls bouncing around. The energy, when they can be transferred from one molecule to another when they collide, but the average kinetic energy of the molecules doesn't change with time. As long as the temperature stays the same, the average energy in the substance in the collection remains the same. It's also proportional to the temperature. We will see that in one of our Odyssey labs, but if you look at this, you can see that at 0 degrees, you have this distribution under the blue line, distribution of speeds, and most of the molecules have some average fraction of the speed, but there are some that are really fast and some that are really slow. Now, if you were at 100 degrees instead of, get that over a little further, instead of 0, you'd see that you have a larger distribution of speeds. The average is at a higher speed, but there's fewer at any one particular speed. This U that you see is the root mean speed, and it is proportional to the temperature. It's called the root mean speed, and it's the speed of a gas molecule having the average kinetic energy. The molecule with the average kinetic energy doesn't land quite at the peak of the distribution. That has to do with the probability and statistics. If you want to think about the difference between velocity and root mean speed, think about the difference between a deviation of a data point and the standard deviation. They're very similar, but slightly different based on the distribution shape of the curve. And this formula down here should look real familiar. It should be very similar to kinetic energy equals 1/2 mv squared. The difference is that this E symbol and the mu symbol are for the average kinetic energy. There's lunch. See you in a little bit. Okay, applying the root mean speed. Let's think about what would happen if the nitrogen molecules in a gas sample are increased by temperature, increased in volume of the sample container, and mixing with some argon. How would that impact the root mean speed? Pause if you need some time to think. Okay, an increase in temperature should increase the root mean speed. The increase in volume should have no effect, because if they have the same temperature, they should have the same energy and transfer it in the same way. Mixing with argon, again, should have no effect. Okay, let's talk about effusion, which is the escape of a gas through a tiny hole into an evacuated space, ideally. Probably doesn't happen all that often. Think about running over a nail with your bicycle and you have air coming out, or your car tire or something. The gas will effuse out of the molecule, out of the container. Now, molecules will fuse differently depending on how large the molecules are. And the difference explains why a helium balloon tends to go flat a lot faster than a nitrogen balloon. You can see the helium balloon lost a lot more air than the nitrogen did, a lot more gas. Why do you suppose that is? Well, it's because the molecules of helium are a lot lighter, and so therefore they will have a relatively faster velocity. So let's derive Graham's law, which compares the relationship between the mass of a molecule and its velocity. So kinetic energy being 1/2 mv squared for both molecules. Let's, just imagine one of them being nitrogen and one being helium. So I can rearrange it so I get the masses of both molecules here on one side and the velocities on the other. And then let's take the square root so that those velocities can be compared directly. So if we say that this is the velocity of the helium over the velocity of the nitrogen, that is equal to the square root of the mass of nitrogen over the mass of helium. Okay, I think it'll be easier if we can look at some actual numbers. Let's try a problem. Let's calculate the ratio of the effusion rates of nitrogen and oxygen. So if we know that the square root of mass of oxygen over the mass of nitrogen equals the velocity of the nitrogen as compared to the velocity of oxygen. So we just derived. So that would mean the square root of 32 grams per mole over 28 grams per mole equals the relative velocity of nitrogen to oxygen. Go ahead and give that a calculation, and you should get, pause if you need to, 1.07 to 1. So nitrogen goes slightly faster because it is slightly smaller. That makes sense, huh? Love it when they make sense. Okay, now diffusion is slightly different. Instead of a gas moving through a tiny hole, diffusion is when the gas spreads throughout a space. All right, let's talk about real versus ideal for a moment. Real gases deviate from ideal behavior because they don't all obey the tenets of the Kinetic-Molecular Theory. In the real world, they only conform to the ideal gas equation when they're at very high temperatures and low pressures. So they don't have as much time to interact and attract and take up space. And some gases deviate more than others. So if you think about this red line here being what an ideal gas would do in terms of pressure versus the rest of the variables, nitrogen has a little bit of deviation, methane even more, and you look at carbon dioxide. Oh, I said that wrong. Carbon dioxide has the most deviation. I'm sorry. Ideal gas has this constant. Sorry, this one up here is hydrogen. Read that wrong. So why do they deviate at different rates? Well, it has to do with their size and their polarity and the different factors that can impact it. So we might want a slightly better equation than PV equals nRT if we're looking at things that are not at high temperature and low pressure. Okay. Here's another graph that might help look at this. Even for the same gas, let's say that hydrogen gas, you show very different behavior at different temperatures. So notice it's most ideal at 1,000 Kelvin. But as it gets colder and colder, 200 K is, not that far from room temperature, but it deviates a lot down here at these low pressures and at the high pressures. What's happening is at different temperatures, you have slower molecules that might attract each other, or at very high pressure, they might start taking up some space if they're in a very cramped volume. So if you look at this picture, you can see how if they're at a higher pressure, as in this piston, they're closer together and the molecules will interact more, repulse, attract, and even take up more space than they do in this lower pressure situation. Okay, so we can adjust the equation to account for some of this behavior. It's called the van der Waals equation, and here it is in all its glory. It's not that confusing. Our normal equation is PV equals nRT, but what's happened here is they've added a fudge factor. A factor to correct for the pressure change that might be caused by some attraction and some volume of the molecules, and to the volume by some attraction in the molecules. So let's try calculating that out. Make sure you've got this equation written down, and we'll come back and get the variables that we need. All right, consider 1 mole of carbon dioxide gas confined to a volume, 1 mole, volume of 3 liters at 0 degrees Celsius. We want to know the pressure of the gas using the ideal gas equation and then the van der Waals equation. Okay, so let's first do it with P equals nRT over V. So we've got 1 mole. And let's find atmospheres. 0.08206 liter atmospheres per mole Kelvin, and a temperature of 273.0 Kelvin, all over 3 liters. So let's check our units. There's our liters, there's our moles, there's our Kelvin, and we end up with atmospheres. And that answer is, if I'm remembering correctly, look at my notes. Oh, don't have it written down. Calculate. Okay, I got 7.467 atmospheres. That's using the ideal gas law. All right, so let's think about carbon dioxide. It's got some oxygens. It's a fairly heavy gas, not polar as a molecule, but it does have polar bonds. So it might be impacted by some of those interactions that an ideal gas should not be affected by. So let's now try doing it with the van der Waals equation. First, we need some numbers from the previous page. So we need that A is 3.59, oops, and B is 0.0427. Write those down. All right, so let's go through this together. So I'm going to rearrange this equation quickly. So I've got P minus N squared A over V squared, equals nRT divided by V minus NB. Hopefully everyone's okay with that. And then to finish this out, if I move this over here, oh, that's a plus. Should be a minus. N squared A over V squared. All right, let's put in some numbers. So we've got 1 mole. I'm going to leave off some of the zeros, but we know we got 4 sig figs here. And A was, no, our value. Sorry, let's do this first. 0.08207 at 273 Kelvin divided by the volume of 3 liters minus 1 mole again times the B value, which was 0.0427. Okay, minus 1 squared times A, 3.59 over 3.00 liters squared. I've checked, you canceled out all the units, and you end up with, according to my calculations, 7.176 atmospheres. Okay, I think I've got the answers here somewhere. Okay, with the ideal gas law, we got 7.467, and with van der Waals, we got 7.176. That's a fairly significant difference. That's about, a third of an atmosphere. And that could really make a difference if you need accurate calculation. So, van der Waals equation, fun to use. You won't ever have to memorize the equation or know the A and B values, but you'd be given them, but know how to use it. All right, that's it for today. See you later. Bye.